So, let's talk about few types of topological vector spaces, the main objective of this chapter, and the separation properties of topological vector spaces. So, as before, let X be a topological vector space, and we have the following properties or types of the topological vector spaces. So, we say a topological vector space is locally convex if it's local based. We just denote it by a curly B, okay? Has convex members. Next, locally bounded. If 0 has at least one bounded neighborhood. So it needs one to be locally bounded. Next, locally compact. 0 has a neighborhood such that its closure is compact. So same as the boundedness, you only need one for it to be locally compact. And next is metrizability, which we've talked before. Metrizable. There exists a metric on a topological vector space such that the topological induced by this metric coincides with the topological it has. And we'll say that the metric is compatible with the topology, just as before. And next, we have a F space, which is a topological with a metric such that D is invariant. Remember that we have an equation for the invariance, right? So the metric is the same if we translate both points by the same vector. So this is what it means. So invariant and complete, which as before means that every Cauchy sequence is convergent, and it will be called a F space. And next we have our main space, or main subject of discussion, the Fresher space, which is a F space that is locally convex. So in short, a Fresher space is a topological vector space with a metric such that it's invariant complete, and also the space itself is locally convex. It will be called a Fresher space. So it's a generalization of Banach space. So next we have a normability. It's normable if exists a norm such that the metric induced by the norm is compatible with the topology. Okay? And we have the norm space that we had defined before. We have the Banach space that we also defined before. Just to find you, it's a space with a norm such that it's complete. So it is a generalized to the Fresher space. As you can see that a norm space is automatically locally convex, as we'll see later. And the norm is automatically invariant as well, as we'll see in the next theorem, which we will prove later as well. We will prove it later in the sections. Finally, we have the Heisenberg property, which says that every closed and bounded set or subset is compact. So this is a very nice property to have, because it almost looks like a closed and bounded set. It's very like finitely dimensional, as we will see later. The locally compact spaces are finite dimensional. So two remarks on the terminology. The terminology F spaces and the Fresher spaces are not universal. Sometimes other author will denote our Fresher space that is locally convex simply by the F space, and simply doesn't have a definition of an F space. We define it here just for convenience. And so for the Fresher space, if you learned about topology before, it is referred as a T1 space, which is very different space from the Fresher space we have, as it is not even Hausdorff. So the Hausdorff space will be a T2 space. T2 is Hausdorff. So you should not be confused with the terminology in topology. They are different subjects. Also, as we'll see, topological spaces are automatically Hausdorff, as every point is a closed set. Okay, so let's state the main objective of this chapter. So we have few properties regarding the above properties. So first we have that theorem. This is 1.9. Locally boundedness implies that there exists a countable local base. So, by the way, I will write infinity as countable, uncountable infinity, and countable infinity sign with a slash denotes finite. So this is finite. And two infinite sets signs denotes uncountable. And so one infinity on top a infinity slashed is countable. This is just some convenient notation of myself. So the first one, local boundedness, implies the existence of a countable local base. Second, metrizable is equivalent to the existence of the countable local base. As we will see later, we can actually construct a metric from this local base, and it will be compatible with the topology. So the normability is equivalent to locally convex and locally boundedness. So as we mentioned above, if it is normable, it's automatically locally convex. So Banach spaces are automatically locally convex. D, if dimension of X is finite, if and only if it is locally compact. And finally, a very useful property, locally boundedness plus the Hagen-Borel property implies the dimension is finite. So let's make a few remarks on these properties. So as we'll see in the later sections, the holomorphic functions on the open set and the smooth functions on the compact sets are Fisher spaces with Hagen-Borel property. Then by E, they cannot be locally bounded, not locally bounded. Hence, by which one is it? C, by C, it is unnormable by C, not normable. So we will see that these spaces are not normable. Also, they also show that the A is not true for the converse. So they are also counterexamples for converse of A. As we will see later. And regarding the which one was it? So we will talk about the LB spaces for P between 0 and 1. And there will be locally bounded spaces that are not locally convex. So that's oh, it's actually not on the list. Okay, fair enough. So, okay, we'll see this example. We'll actually prove that if A is a convex subset of this LP space, then, such that A is convex, this will imply that it is the whole space. We will see this later. So let's move on to the separation properties of the topological vector spaces. So let's start with the theorem, such that if we have a compact set and a closed set, which are both subsets of the space, then there exists a neighborhood of 0, of course, such that they can still be separated. Oh, I missed a condition that they not intersects. So that's added here. K intersects C is empty set. So if K is compact, C is closed, and they does not intersect, then there will be a little bit space to wiggle, like something like this. So we can add a little bit, something like that. And they will not intersect still. So this is the first theorem we are trying to prove. So we prove this theorem first by showing a convenient property. So for every neighborhood W of 0, we want to show that exists V, also a neighborhood of 0, such that V plus V contains in W, which is very easy. Since this is continuous and 0 plus 0 equals 0, then by the definition of a continuity, there exists V1 and V2 such that V1 plus V2 are contained in W. So the V here we are required to be a balanced set. Not quite. We don't need to be a balanced set. In fact, it's only symmetric in the sense that the minus V is equal to V. So as we will see here, we just let the neighborhood V be the intersection of V1, V2, minus V1, and minus V2. Then this neighborhood V will be the desired neighborhood that we are looking for. So if we apply this little property here, let's call it star. Applying star twice, we get V such that sum of 4 V's can be contained in a neighborhood W. So okay, let's start. If the compact set K is actually empty, then there's nothing in this set. So we have nothing to prove. So we better just assume that it's non-empty. So if it is non-empty, we then pick any point in this compact set K. Then we apply the lemma above as, so apply star with X as origin as 0, and the complement of the other closed set in the assumption, the other closed set, this one, the complement of C as the neighborhood W. Then we obtain a neighborhood Vx such that sum of 4 Vx lies inside the complement of C, which is equivalent as saying that X plus 3 of these, because X lies inside it, X plus 3 of these does not intersect C. So once we find this, let's use a little property about the sets. We can actually prove that. So if A plus V intersects B is empty, if and only if A intersects B minus V is empty. And the proof is very easy. If they intersect, you can find AVB. That's it, find these, then it will equivalent as this. So obviously they are equivalent. So we can, from this equation, we can move one Vx to the right. It will still be empty. And because Vx is symmetric, in the sense that minus Vx is equal to Vx, so we can actually just write plus here. So after doing that, we can actually cover the compact set K. That, so since xi plus vxi so for xi belong to K is a open cover of K, and K is compact. So let's write it this way. So there exist points xi's I from 1 to m such that K is contained in the union of these neighborhoods. And we define a neighborhood V by the intersections of these neighborhoods. So Vx1, Vx2, all the way up to Vxm. And because we have an extra Vx here, we can actually still cover this K. So remember that the K is covered by the neighborhoods xi plus vxi, and it will still be covered if we plus v, right? Obviously. And by the previous property that we just proved, O of these does not intersect V, as this is actually a subset of and by this, let's call it 1, by 1, oh, I forgot to plus a V here. So K plus V intersects C plus V will be empty. So that proves the theorem. And a quick remark, since the set C plus V is open, so replacing the K plus V by its closure still holds. I mean this equation. So if you write it out, it looks like this. K plus V taking the closure intersecting C plus V is still an empty set. And this will implies the following theorem. So theorem 1.11, which says that if B is a local base, then for every neighborhood, every member U belongs to B, there exists, let's call it V, such that U contains the closure of V. And this is very easy. We just apply the above theorem, above 1.10, with C equals to U complement and K be the origin. Then we'll find a V, right? And the V will be the same V as here. So the closure of it intersects and this is equivalent as saying that the neighborhood U contains the closure of V. So we immediately obtain this. This will be useful later. And finally, if we use the fact that every point is closed, which is theorem 1.12, we have that every topological vector space is Hausdorff. So again, by applying theorem 1.10 with K be a single point and C be another single point, we obtain a neighborhood such that these two neighborhoods separates X and Y. So the space is Hausdorff. Okay. And we'll talk about some properties of interior enclosures